Coursera course, Constant Velocity Lab 1. Our objectives are discuss Newton's second law of motion, extract constant model from tracker, create a constant model from VPython, make a graph comparing tracker and VPython, and answer the following questions. Now we're going to discuss Newton's second law of motion. Final velocity equals initial velocity plus net force divided by mass times delta time. We can simplify this equation by taking mass and multiplying it by final velocity and initial velocity, giving us a new equation that it will be mass times final velocity equals mass times initial velocity plus net force times delta time. Multiplication of the velocity times mass in both sides will give us a new vector known as momentum. We replace momentum in the Newton's second law of motion and get the momentum principle, which will be final momentum equals initial momentum plus net force times delta time. Now I'm going to show a video which I recorded for creating the tracker's constant model. This I place my coordinate plane so the ball moves across the x-axis, as you can see, positive x-axis. Now we're gonna find velocity and of the ball for which we need initial time, initial position, a final time, and a final position. I recorded all the data from tracker's graph. Knowing this, we can apply the velocity formula, which will be v equals delta t over delta t. We then replace the values and get our velocity. We write it in component form. Well, now with all this data, we're gonna replace it in VPython. I manipulated the ball and the track color in VPython for my pleasure. Yes, my pleasure. So as we place the recorded data in Python, we got that the ball's initial position is in the vector is 0, negative 0.001, 0, and the ball's velocity is the one we just calculated, that is 1.47. Also, we chose to start the clock at 0 seconds. As we keep moving, we get here to the part where the calculus is made. Well, what this does is repeat a process under some restrictions which we manipulate. This tells us that the process will be repeated only when the time is less than 0.63. Why did it choose 0.63? Well, that's because as this is a model of a video, it must be as accurate as possible so the tracker can take a final time and go. So we take a final time from tracker, take it to VPython, and write a close number to the one you got in your time, so that the video and the graph will be like yours in the tracker. Having all this, we now are able to run the model. Run the model. Absolutely perfect. You can observe how VPython has created a video similar to mine and the graph too. I've copied the data from tracker in an Excel worksheet. My data from Python and my data from Python 2, creating a comparing graph between both. As you can see, my graph is a little deviant, well, really not too much, from Python's initials ideals graph. Well, that's because the ball moved a little bit to the left, but it follows the path. As you can see, my graph, VPython is a black line behind the blue line, which is trackers. Finishing this leads me to answering the two final questions. Question number 1, Mr. Potter. What if, when you analyze the video in the tracker, if you were able to flip the orientation to the axis, how would they remain the same? Well, the graph would not remain the same. Everything else would. The graph will be in tracker. In tracker, the graph will be from the upper left corner to the bottom right corner. Nothing would really change, except the displacement will be negative to the left in the x-axis. Question number 2. What does it mean? Your observations can be predicted well by your computational model when you set the net force equal to 0 in your model. Is it possible for you to say how many pushes and pulls are added together to give 0 net force in the cases you just observed? Well, the only two things influencing my video, which I'm about to show, my video that I'm about to show, the only two things influencing that kick will be gravity, friction, and air resistance. Well, thank you all, and I'll see y'all later.